let's dive in. Today, we're cracking the secret code of one of the most perfect shapes in all of mathematics. We're not just looking at a circle, no, we're going way deeper. We're about to read its biography, its entire identity, written out in the universal language of algebra. So, here's how we're going to break it all down. We'll start with the circle's fundamental code, the thing that makes it a circle. Then we'll see how to give its equation a major power-up so we can solve some really cool geometric puzzles. This isn't just about memorizing formulas, It's about seeing how one simple shape holds the key to solving some surprisingly complex problems. Okay, first things first. How in the world do you take something you can draw with a compass, something so visual, and describe it perfectly using just symbols on a page? But before we even get to the algebra, let's back up. I mean, we all know what a circle looks like, but what is it really? What's the one unbreakable rule that every single point along its edge has to follow? Well, the answer comes from this idea called a locus. Now, that might sound a little fancy, but it's really simple. It's just a path made by a point that's following a very strict rule. And for a circle, the rule is beautiful. It's just this. Every point on the path has to be the exact same distance away from one single fixed center. That's it. That's the core identity of every circle in the universe. And this, right here, is that simple rule translated into the language of math. This equation is literally just saying that for any point on the circle, which we call x, y, the distance between it and the center, a, b, is always going to be the radius r. It's like the circle's birth certificate. Okay, so that first equation is great if you already know the center and the radius. But what happens when you don't? What happens when the circle itself is the mystery you're trying to solve? Well, for that, we need to unlock a new, more powerful form of the equation. Think of it like this. We're taking a standard engine and tuning it for high performance. First, we expand all the terms out. Then, we shuffle everything around into a nice, neat order. And finally, here's the clever bit. We've replaced some of the clunkier parts with three new, sleek variables, g, f, and c. It's a little algebraic trick that makes the whole thing incredibly flexible and ready for action. And just look at the result of that tune-up. Over on the left, you have the basic form. Simple, gets the job done. But on the right, that's the general form. Think of this as the superhero version. Yeah, it looks a little more complex, but those new letters, G, F, and C, are secretly holding all the circle's information, making it the perfect tool for when you have to work backwards from clues to find the circle itself. So we've got this superpowered equation. What's it good for? Well, let's throw it at its first big mission. A classic puzzle that would be a nightmare to solve without it. I want you to picture this. Take any three dots on a piece of paper, as long as you can't connect them with a single straight line. There is one, and only one, perfect circle that passes through all three of them. The big question is, how on earth do you find it? And this is where our general form just totally shines. We take a tricky geometry puzzle and turn it into a straightforward algebra problem. See, since we know each of these points lies on the circle, their coordinates have to work in the equation. So we just plug in the x and y values for each point, one by one. And what do we get? Three different equations that all share the same three unknowns, our friends G, F, and C. Now, we're not going to get bogged down in all the algebraic heavy lifting of solving these equations. The main takeaway here is that it's a solvable system. And when you run the numbers, the first piece of the puzzle just falls right into place. We find out that G has to be -1. And knowing that helps unlock the next piece of the puzzle. It turns out F must be -3, which finally lets us solve for the last constant, C, which is 5. Just like that, we've cracked the code. So all we have to do now is plug those solved values for G, F, and C right back into our general form. And boom, there it is. That is the one and only equation for the circle that perfectly connects our three mystery points. Mission accomplished. All right, so we've mastered finding a circle. Now what happens when our circle encounters another shape, like a straight line? Can we use algebra to predict what their relationship is going to be without even having to draw anything? Well, there are really only three ways this can play out, right? The line can slice right through the circle at 2 points. We call that a chord. It could just graze the edge, touching at exactly 1 point. That's a tangent. Or it could just miss the circle completely. So how can we know which one it's going to be? Is there some kind of mathematical crystal ball we can use? Well, turns out there is. It's this awesome little tool from quadratic equations called the discriminant. When you combine the equations for the circle and the line, you get a new equation, and the discriminant of that equation tells you the future. It tells you exactly how many intersection points there are.
And here's the beautiful part. The rule is so simple. If the discriminant is a positive number, you've got two intersections, it's a chord. If it's exactly 0, you get one intersection, a perfect tangent. And if it's negative, they don't touch at all. No guessing, no sketching. The algebra just gives you the right answer every single time.
Okay, a circle and a line is one thing. But what happens when you bring two circles together? Well, the relationships get even more complex and, honestly, even more interesting.
I mean, they can just touch on the outside at one point, or they can overlap and intersect at 2. One can even be tucked neatly inside the other, touching internally. But maybe the coolest relationship is when they're orthogonal, which just means that where they cross, their tangents form a perfect 90-degree right angle. And you guessed it, every single one of these scenarios has its own algebraic test.
So, we've been on quite a journey here, haven't we? From the absolute basics of what a circle even is, all the way to solving some pretty tricky geometric situations. So let's just zoom out for a second and ask the big question. Why does any of this matter? For me, it all comes down to this. This is the real magic of what we've been doing. We took a shape, a visual idea, and we translated it into the pure language of logic and algebra. And once it was in that language, we could play with it, combine it with other things, and ask it questions that revealed secrets we never would have seen just by looking at the picture. And that's the real power, isn't it? The humble equation of a circle is just a beautiful reminder that math is the language we use to make sense of our world. From the orbits of planets to the design of tiny gears, it really makes you wonder, what other secrets of the universe are out there, just waiting for someone to find the right equation to describe them? Thanks for digging into this with me.